Today we're going to talk about an introduction to conic sections, and we are actually going to focus on two of the four conic sections, and those are going to be the circle and the ellipse. We do have these four different types that you can end up with when you are working with the intersection of a plane and a cone. So we've talked a lot about a parabola already. Some kind of cool things that can happen with conic sections is you can end up with parabolas that are not functions. So you can end up with the sideways parabola as well as your traditional vertical orientation for the parabola. You can also get something that's really cool called a hyperbola, where if we have two cones that are positioned in such a way and you intersect those two cones with a particular plane, you can end up with this shape right here, which is called a hyperbolic shape. We are not going to go into any kind of depth with the parabola and hyperbola. However, I will give you guys some resources in Connect Math if you are interested in just looking at the other two types of conic sections. We are going to focus on the circle and the ellipse. So you can kind of think about a cone here, and if that plane is intersecting parallel to the base of the cone, you're going to end up with a circular section. And if you take that same plane and you intersect it at an angle, you're going to end up with an elliptical type shape. So those are the two that we are going to focus on this semester. So let's start with the definition of a circle. So this is your textbook definition here. So a circle is a set of all points in a plane that are equidistant from a fixed point called the center. The fixed distance from any point on the circle to the center is called the radius. So I have just a circle here drawn, and so we can kind of just maybe label some important things here. So we have the center that's going to be, of course, in the center, and then a radii, or the radius, is going to be that distance from the center to any point. So there are infinite number of radii in a circle. All of those would be a radius. And then note that if you have something that is going from end to end that goes to the center, then that would be called your diameter. The diameter, of course, is twice the length of the radius. So let's just start with kind of just thinking through and looking at something. So if we're going to plot the point 0, 0, and we are going to graph all of the points that are going to be 5 units away. So there's my starting point. So if I do 5 units away, I'm going to do all the easy ones. So I'm going to do all the vertical and horizontal points. And then if I actually wanted to graph everything that's 5 units away, this would actually make a lovely circular shape. Because what that means, 5 units away, is that you would have a radius of 5. And then that puts the point 0, 0 as the center of my circle. So let's take this same idea and let's actually see if we can't generate an equation that's going to represent all points that are going to be 5 units away from the origin. So let's look back at our picture here. If I want to generate an equation that's going to be all of these points that are 5 units away, what I can think about maybe is the Pythagorean theorem. So if I'm going to have this hypotenuse right here, so I'm just going to kind of draw an arbitrary hypotenuse on this in this picture, I know that that's going to be 5 units away because that's going to be the length of my radius. Now, whatever this horizontal distance that we're going to be going in order to meet up with that radius, that would be, say, let's just call it x. It's going in my horizontal direction, so that's going to be x. And then whatever this vertical distance to get to that distance of 5 is going to be y units away. So if we have this nice little lovely right triangle right here, we can use the Pythagorean theorem to go ahead and relate those values. So this would be x squared plus y squared equals 5 squared. Remember, the Pythagorean theorem is a squared plus b squared equals c squared. Now, really the only simplifying I have to do here is I can just clean up 5 squared. So this is actually an equation that's representing a circle with the center at the origin and a radius of 5 units. Now I have a few pictures on your note sheet here, and so I have 4 different circle equations with 4 different circles graphed. So note each of these circles are in different quadrants of the coordinate plane. So I'll kind of add a little bit of detail there so you can specifically see which quadrant each one of those falls in. So looking at this first equation, notice we have 2 subtraction signs with our x and our y value here, and then we have it set equal to something over here. And let's just kind of look at it. Let's see if we can maybe kind of generate some ideas here. So if I'm looking at this circle, it might be kind of important to identify where that center is. So it looks like that center is falling right about there. And that's putting my center, if this is going to be in the first quadrant, that's putting my center at the point 3, 2. And then let's see if we can identify the length of the radius. So if I'm going out, going from this point down here from where my center's at, and it looks like I'm going 2 units away. So this circle has a center at 3, 2 and has a radius of 2. If I look at the next one, I'm now looking in this second quadrant, and it looks like my center is now at -3, +2. And my radius is still, it looks like 1, 2 units away. So you can kind of see where the 3 and the 2 are in the equation, and then maybe how they got that 4 with the radius being 2. Let's look at the last 2 examples here. So now I'm in the third quadrant. So it looks like both of my center coordinates are negative. I've got the center at -3, -2, and I have a radius at +2. My last one is in the fourth quadrant, and this center is at +3, -2, and my radius is still 2 units. So this brings me to the 2 different forms that we can have for a circle. So the standard form is most definitely the form that you want to be working in, because this is the form that gives us all of the information. The center is at the ordered pair HK. So notice it's going to be the opposite sign, and we kind of saw that in those last ones. If this is x minus h, that means h is going to be the opposite of whatever value you have here. And then k is also going to be the opposite of whatever we have here. And then our radius is going to be r. So this value right here is always squared. So we need to take the square root of that number in order to identify what the radius is. Now, the general form gives you 0 information in its current state. So again, I'll give you some information to link to Connect Math if you want to see how you can complete the square 2 times in order to take something that's in general form and rewrite it in standard form so you can easily graph and identify the important information from the circle. So let's look at a few examples. So let's go ahead, write the equation, and we're going to graph this as well with this given information. So we're going to have a center at -2, 5. So I definitely want to start there. And then I'm going to have a radius of 1. So I'm as fancy as just going 1 point out in each of those 4 directions and then just trying to draw the best circle that I can. Connect Math will have you use a tool. It's pretty easy to work with. Again, just let me know if you have any questions on it. I'd be happy to meet with you to troubleshoot anything with Connect Math. So now let's actually write the equation given this information. So if our center is at -2, 5, -2 is my h coordinate and k is my 5 coordinate, and then my radius, so my r value, we're going to plug in 1. So I'm going to have x minus -2 quantity squared plus y minus 5 quantity squared equals 1 squared. And now my next step would just be to go through and do some cleanup work. That would clean up to give me x plus 2 quantity squared, y minus 5 quantity squared, and then 1 squared would give me 1. So there's my equation, and then there's the graph to go along with it. Let's look at another one, center at 0, -1 with a radius of 10. So find 0, -1, and a radius of 10. So this is going to be huge. And then I'll just kind of sketch in my circle here. Now let's write the equation. So if the center is at 0, -1, this would give me x minus 0 quantity squared plus y minus -1 quantity squared equals 10 squared. And then I can just go through and I can clean this up. So we're going to get an x squared. This is going to end up with a y plus 1 quantity squared. And then 10 squared you'd want to write as 100. All right, go ahead and take a moment. Try these 4 questions, or these 4 problems, and see how they go. Hopefully they're pretty smooth. Circles are really, really nice to work with. There's not typically a whole lot of guesswork or anything when you're trying to work with them. All right, hopefully you had a chance to do these. So let's look at the equation for number 1. So center at -1, 5, and a radius of 7. So this would end up being x plus 1 quantity squared after you cleaned up minus a negative, plus y minus 5 quantity squared equals r squared. So that's going to end up equaling 49. Now, the only difference with number 2 is that you have just an uglier looking radius, and that's totally fine. We really don't care a whole lot because you're still going to square that number. So root 7 squared is still going to give you just a positive 7. So that's what your equation would look like. For 3, we're going to identify the center and the radius. So our center for 3 means I just need to take the opposite of what I'm given. So this is going to be 4, negative 2. And then my radius is going to be the square root. Don't know why my pen is not working now. The radius now is going to be the square root of 25. So my radius will be 5. And if I'm going to graph this, find the point 4, negative 2, and then just go out 5 units in either direction. And there's our circle. For B, the 28 is going to be a little bit funky. We're going to have to do our best estimating here as we graph this. So our center, if there's nothing with the x-coordinate, that puts our center at 0 for the x-coordinate. So this would be at 0, negative 7. And then our radius is going to be the square root of 28. So I am going to go ahead and break this down just to make this radical simplified. So root 28 could be broken down to root 4 times root 7. And we know the square root of 4. So root 28 is equivalent to 2 root 7. So I'm going to find my center at 0, negative 7. And then for this one, the square root of 28 is just a little bit bigger than 5. It's 5 and some change. So I'm just going to have to do my best guess as to what that's going to be. So 5 and some change in either or in all directions here. And then I can connect the dots in my circular shape. All right, last thing here for circles is let's just look at some of the essential questions with circles. So I have an equation for you. Let's go ahead and graph it. So for this particular equation, we're going to have a center at 4, 0. And we are going to have a radius of 3. So here's my circle. Now, is this circle a function, or is any circle a function? And the answer here is a big fat no. So when we get to conics, this is the only time that we are working with things that are not going to be functions. For each input, notice there are multiple outputs. If I put in an input of x equals 4, notice I get a y value up here and a y value down there. So we are not a function because each input has multiple outputs. Now let's determine all of the intercepts. So notice I could actually quite easily go ahead and just look at these graphically, but just kind of keep in mind we have all this equation solving skills under our belt. So let's look at finding the x-intercepts graphically, or sorry, algebraically. So we're going to have y equals 0. So wherever there's a y, I'm going to plug in 0, and then I'm going to go ahead and solve this equation. So this gives me x minus 4 quantity squared equals 9. Now to get rid of squaring something, because that is isolated all by itself on that side of the equation, I can go ahead and square root both sides. So that leaves me just with x minus 4. And then the square root of 9 gives me positive 3 and negative 3. So now to get x all by itself, let's go ahead and add 4 to both sides. And then this is something I can clean up. These are like terms. So I have 4 plus 3, which is 7. And then I have 4 minus 3, which is 1. So my x-intercepts would be the 0.70. And then the 0.10. And of course I can graphically confirm that. And then let's look at the y-intercepts. Graphically, it doesn't look like there's any y-intercepts on here. So let's see what's going to happen. I guess I'll kind of move up here. So for the y-intercept, that's when x equals 0. So let's go ahead and plug that in. So we are going to have 0 minus 4 quantity squared plus y squared equals 9. So 0 minus 4 is negative 4. Negative 4 squared is 16. So we end up with 16 plus y squared equals 9. If I'm looking to get y squared isolated, when I take away that 16 from both sides, that leaves me with a negative 7. Now notice when I square root both sides, I am now taking the square root of a negative number. I am not working in the polynomial unit, so this is a non-real answer. So there are no y-intercepts, no real y-intercepts. And of course, graphically, we can confirm that. For 4, let's look at the domain for this problem. So which x values work? Well, it looks like my smallest x value is 1 and my largest x value is 7. And then my range, my smallest y value looks to be, I think that's -3. And then my largest y value, whoops, is +3. Sorry about that. I hit the wrong key. I wasn't looking. And then lastly, what type of symmetry do you see within this circle here? Well, this particular one, whoops, I moved it. Unfortunately, wow, this is going well. My center was 4, 0. The symmetry that we have here is we have symmetry with respect to the x-axis. All right, so that's everything you need to know about circles. Let's talk about an ellipse. So an ellipse is going to get a little bit crazier because we're going to be introducing some foci as part of our definition here, and so we will be finding those. So here's our definition. An ellipse is a set of all points x, y in a plane such that the sum of the distances between x, y and two fixed points is a constant. The fixed points are called the foci of the ellipse. So let's take a look. I've got a little applet here. And so what we have here, so notice it said it's a fixed distance. So here's my elliptical shape. So these fixed points right here. Notice the F1 is fixed and the F2 is fixed. And we have these particular, if we take, I don't know, think about like these, the two F points being a string, and we're pulling it taut, and that's where the point P is. If I were to move this point P all the way around, it's going to trace this elliptical shape. So you could actually make a perfect ellipse with two thumbtacks and a piece of string, so long as you maintain that tautness of the string and you're able to go all the way around. So for this particular one, they just have an arbitrary 16. So they set those two distances. If they add those two distances together, it always remains the same. So that's what an ellipse is. That's our definition of an ellipse. So let's give you some information here. So we're going to have the standard form of an ellipse, and I'm actually going to give you two different forms here because it's going to depend on the orientation. So this particular ellipse right here has a major axis that is horizontal, meaning this is going to be a long ellipse. It's going to be longer than it is tall. So let me give you a few pieces of information here. We have kind of the same setup as what we saw with the circle. We have x minus h quantity squared and y minus k quantity squared. So that's the same. So we are going to have this center at hk, so that's not any different. And then I want to talk about the a, the b, and the c value right here. A is always going to be the bigger number, so whichever one has the bigger number, like if the bigger number is underneath the x or the bigger number is underneath the y, that is going to determine the orientation of your ellipse. So for this particular picture, A is going to be the bigger number because from that center, you are going A units to the left and to the right. That's what's happening. So we're going to say A is the distance from the center to the vertices. So this one has two vertices. So there's a vertex here, and then there's a vertex here. So that's going to be your distance. So you can go from your center, you're going to add the A value to it, and then you're going to subtract the A value from it to find those two vertices. The B value is going to be your distance from the center to the endpoints on what's called the minor axis. You're going to see that vocabulary in Connect Math, and then as you're plotting these, you're going to see it labeled as the co-vertices. So co-vertices mean they're just not the dominant ones. So right here, this would be a co-vertex, these 2 points right here, because they're not determining the overall orientation of this ellipse. So those are your co-vertices. Also, because this is the shorter of the two, they call that one the minor axis. The big one is the axis right here, so this would be the major axis. Now, for the C value, C is used to find the location of the foci. So foci is the plural for focus. And remember the ellipse, these 2 points right here, these 2 pink dots, those are the foci. This is your C value. So this C right here is a distance. So from our center, after we find out what C is, we're going to go from our center and we are going to add C and we're going to take away C from that center coordinate. And the way we find C is actually a relationship based on the Pythagorean theorem. It's going to be C squared equals A squared minus B squared. So it's an easy computation to work with. You might get nice numbers and you might get ugly numbers. It just kind of depends on what numbers you're given in the problem. So standard form here. So notice everything is exactly the same, except now our major axis is going vertical. So the Y value is now going to have the bigger number underneath. So notice this right now is going to be my major axis. So this would be a vertice, or the 2 vertices, and now the horizontal ones would be the co-vertice for those 2 sides. So just to kind of keep the terminology the same, is just this is what's different. All right, here's our general form for it. Again, if we were in class, you know, kind of with our normal schedule and everything, we would definitely be working with things in general form as well. But that is something that we are not doing this time. But I will certainly point you to some resources in Connect Math if you are interested in doing that. So let's look at a few examples. So Connect Math is going to have you do these 5 things, and I promise they're really not that bad. So let's just kind of go through them. So we're going to identify the center of our ellipse here. One thing to note with both of the standard forms here is these are always set equal to 1. So that's always something to look for with your equation. If it's not set equal to 1, you're going to need to take your time or take some time and get it set equal to 1. So to identify the center of our ellipse, this is actually going to be pretty straightforward. It's going to be just like with the circle. So our center for this one is going to be the opposite here. So that's going to be +3, and then the opposite here. So -4. And I'm actually going to identify a lot of the information from my graph. So I'm going to go ahead and plot the center. So here's the point 3, -4. And now let's go ahead and identify the vertices. So I need to look at the numbers associated with this ellipse to determine what my orientation is, to see which set of endpoints are going to be my vertices. Because 25 is bigger, I know this is going to have a horizontal orientation, meaning it's going to be longer than it is wide. Now, to identify these vertices, I need to travel A units, in this case from the right and the left of my center. So if this is A squared, this tells me that A is going to be equal to 5. So I'm going to go 5 units to the right. There's a vertice. And then I'm going to go 5 units to the left. There's my other vertice. So directly from my graph, I'm going to go ahead and identify my vertices, because now I can just identify what those ordered pairs are. So it looks like -2, -4, and 8. -4. Now, identify the endpoints of the minor axis. So that's going to be my B value. So up here, this is B squared, remember? So that tells me B is going to be 4. So in this case, it's going to be 4 units up and 4 units down from my center. And then these would be the endpoints of my minor axis, also known as the co-vertices. So for my co-vertices, or also known as endpoints of the minor axis, I can just now look at my graph and identify those points. So this looks like the point 3, 0, And then the point, it looks like 3, -8. All right, for D, identify the foci. So the foci are always going to fall along the major axis. So I know my foci, wherever it is going to fall somewhere, the 2 points are going to fall somewhere along that highlighted line. So to help me find that, I'm going to use the c squared equals a squared minus b squared equation. Now, all I really know is a squared is always the bigger number. And remember, these are given to me in their squared form. So I'm just going to take the bigger number minus the smaller number. And that's going to be set equal to c squared. So 25 minus 16, I'm pretty sure is 9. We get c squared equals 9. Now, when I square root both sides here, I do get positive or -3, but since it's going to be a distance, -3 does not make sense to be a distance. So I'm only working with the principal square root here, so I only want c equal to +3. So that's what my c value is. That is not my foci. My foci is 3 units away from the center. So here's the center. And again, we have that orientation that's horizontal. So I'm going to go 1, 2, 3. Here's a foci. And then I'm going to go 1, 2, 3. Here's my other foci. So those 2 points right there are actually the location of the foci. So it's an ordered pair. So now I can just look at my graph. It looks like 0, -4, and then 6, -4 for the location of the foci. Now, to do the last part, just to graph this, I actually have all the work here. I just need to draw my elliptical shape. So it's going to look something like that. All right, let's try another one. So we are given that this is going to be an ellipse, but it certainly doesn't even come close to looking like an ellipse right now because this is set equal to 81 and not to 1. So what we can do then is divide everybody by 81. So this would give me x squared over 81. Now, 9 divided by 81, that would simplify to 1/9. And I can be lazy and not put the 1 up there in the numerator. And then 81 divided by 81, that is equal to 1. That's why we chose to divide everybody by the 81. So this is our new equivalent equation that we want to work off of to identify all of our important information. So let's graph this one now. So the center of this one looks like it's going to be at 0, -1. And I'm going to go ahead and plot that point real quick. And then let's identify our vertices. So this is where I want to go ahead and look at it. The 81 is definitely the bigger number here, so we're going to have the same orientation. We're going to have a horizontal orientation here for our ellipse. So from my x-coordinate of my center, I'm going to go 9 units to the left and to the right, and those are going to be my vertices. So I can go ahead and label those. So we're going to have vertices at -9, -1, and then at +9, -1. The endpoints of the minor axis, well, let's look at our equation. So my smaller number, my b squared value is 9. So that tells me my b value is going to be 3. So I'm going to go 3 units up, and I'm going to go 3 units down. So these right here are my co-vertices, also known as the endpoints of my minor axis. And I'm just going to, again, from my graph, I'm just going to read those points. So 0, 2, and 0, -4. Identify the foci here. So again, I need to find my c squared value. So c squared is going to equal the bigger minus the smaller. Again, because the 81 and the 9, those are in the equation as a squared and b squared. So then c squared equals 81 minus 9 is going to be, I think, 72. And then we need to simplify 72 because I am taking the square root of both sides. So this looks like it's going to be a pretty terrible number here. So we have the square root of 72. So we want to keep this exact when we actually enter this into Connect Math because this is something that we can keep the exactness on, and then we will approximate it on the graph here. So 72 I think would break down to what, 9 times 8? Nope, 36 times 2. So root 36, we know that is 6, root 2. That's my c value. Now, to keep this in mind of where this foci is going to be, or where these foci are going to be located, root 72 is going to be between 8 and 9. So if we want, we can just kind of sketch that on the graph. You don't have to sketch the foci on Connect Math, but just to kind of see where it is and just to make sure your math is okay. So it's between 8 and 9, so it's going to be somewhere there and, oh, somewhere there. I approximated it there, but the actual location from the center to each of the vertices, we went 6 square root of 2 units. So from that x coordinate of the center, we're going to add 6 root 2, and then we are going to subtract 6 root 2. So if that x coordinate is 0, my foci are going to be located at 0 plus 6 square root of 2 units. And then notice my y coordinate is exactly the same, so that's going to stay at -1. And then we also have 0 minus 6 root 2, comma, -1. Now for each of these we would want to clean it up. Because I can do 0 plus 6 root 2, that would clean up to give me 6 root 2, comma, -1, and then -6 root 2, comma, -1. Those would be my 2 foci points for my conic. And then we can just go ahead and sketch the rest of this ellipse. There we go. All right, one more example. So this one, again, nothing crazy. It's set equal to 1. So let's identify our center here. So our center looks like it's going to be at 0, -4. And I'm going to go ahead and plot that. This one, I'm noticing the y coordinate has the larger number. So I might just make a little mental note off to the side that I am expecting this to be a vertical orientation. So now when I identify the vertices, the vertices will be from the bigger number. So that means I want to look at that 64, and that tells me I'm going to go 8 units up and down from my center. So this guy is a vertice. And then down here it looks like -12 would be a vertice. So my vertices are at 0, 4 and 0, -12. For the endpoints of my minor axis, that tells me I'm going to be going 4 units from the x coordinate. So I'm going to have a covertice here, and I'm going to have a covertice there. And so again, just for my graph, I'm going to read those ordered pairs. So -4, -4, and it looks like 4, -4. For the location of my foci, this will be c squared again equals a squared minus b squared. So this is going to be big minus small. 64 minus 16 is going to be 48. And then I would be square rooting both sides. So I'm going to have the square root of 48, which would break down to give me 16 times 3. So this would be 4 square roots of 3 is going to be my c. So for this one, we are going to go 4 square roots of 3 units. So square root of 48 is just a little bit bigger than 7. So that's going to put a foci here and a foci about here. So the actual location, again, think about this from your center. You are going 4 square root of 3 units up and then 4 square root of 3 units down from your center. So the location of my foci, if my y coordinate is -4, that means my x coordinate's not changing, and then I'm going to have -4 plus 4 square root of 3 for 1 point, and then I will have -4 minus 4 square roots of 3 for the second point. Because again, from that y coordinate, I am either adding or subtracting 4 square roots of 3. Connect Math will have you enter these in individually like this. Of course, if this was like a handwritten assignment or whatever, you would be welcome to do -4 plus or minus 4 square roots of 3 here to indicate that those would be the 2 ordered pairs corresponding to the foci. So lastly here, we are just going to play connect the dots. And that would be my ellipse. All right, so your homework is going to be with Connect Math, going through questions just like this. Hopefully I have all the exact parts that are needed. And again, let me know if you have questions on how to use Connect Math, because you will see this on the quiz and then of course on the final. So good luck. Let me know.